Back in February of 2019, I released a video entitled Building My Dream Computer, and in that video I made the case for making a modern 8 or 16-bit computer made from all off-the-shelf components. Since we don't have the rights to the Commodore brand name, I had given it a temporary code name of Commander 16. After all, Commander has the same number of syllables and same number of letters, and the two words actually have similar meanings. Despite being a temporary code name, the name turned out to be quite popular, so we decided to keep it. However, we were concerned about people abbreviating it to C16, which might be easily confused with the Commodore 16, which is a very different product. So we changed the name to Commander X16 so that people would abbreviate it X16 instead. And so I'm going to try to give you an update on what has transpired over the last 6 months. And the first priority was to find a working video chip, even if it was only temporary. In the last video, I showed the Gameduino being used in a little adapter card on the user port. This actually worked fine, and it allowed me to do some experimentation with low-level SPI programming as well as kernel development. Kevin ended up making a custom board for me that had the Gameduino integrated onto that board. And I was able to get the board working on the C64, and with slight modifications to the code, I also had it working on the VIC-20. The graphics capabilities of the Gameduino are far superior to the Commodore 64, which was one of my requirements for a video chip. However, it did lack a true bitmap mode, which concerned a lot of people. I wasn't terribly concerned since it had so many sprites that you could use them together to create a pseudo bitmap mode for those sort of games that needed it. Still, this wasn't the biggest hurdle to overcome. The biggest problem was speed. It uses an SPI interface, which is not ideal for an 8-bit system. I had asked the community if anyone could modify the Gameduino to work on an 8-bit system bus, and there were a few volunteers for the job, but it turns out the Gameduino was designed on an obsolete Spartan 3, and not that many people were familiar with it. And so this product hung in the balance for some time as to whether or not it would be the final video chip. Another problem we faced is with the 65816 processor. I had originally said I wanted to use this processor because it had a 24-bit address bus and could therefore address up to 16 megabytes of RAM. However, this presented another problem. You see, the 6502 has 16 address lines. These are the lines that it uses to tell the rest of the system which byte of RAM it's currently working with. And it has 8 data lines. Now, these are the lines that allow it to read and write to a byte of RAM somewhere in the system. Well, let's look at the 65816. It has the same number of pins as the 6502, and it also has 16 address lines and 8 data lines. But in order to access 16 megabytes of RAM, it should technically have 24 address lines. So where are they? Well, it shares them with the data lines. Yes, these 8 data lines alternate during the clock cycle to be data lines or the upper 8 address lines, and this behavior is extremely annoying and requires a lot of external circuitry to decode this and split it out. The board had already gotten complex due to this, but things continued to get worse. You see, I never really wanted to use any FPGAs on the system to begin with, but I conceded that we would have to for the video chip. But before long, some of the guys working on the board design ended up having 3 FPGAs on the board, along with all other sorts of complex things like DMA controllers. And at some point, I just started to feel like this project had allowed feature creep to spiral out of control, and it really no longer resembled the system I originally wanted. I also had a strong belief that this board would wind up stillborn. To illustrate the problem, imagine you have 10 components, and you can't test component A without all of the rest of the components working. And you can't test component B without all of the other components working, and so on. And this means that if you make any mistake anywhere, the whole board won't work, and it'll be impossible to figure out which part is not working. At this point, I was really becoming skeptical that this project was ever going to work, and even if it did, it really no longer lined up with my original goal. And just to reiterate, I wanted a computer that was similar to the Commodore 64, but made from all off-the-shelf components and, probably a little bit more powerful. Then one day I was cleaning up my studio room and I came across this VIC-20 motherboard I'd been using to test chips in a few months earlier, and I started to look at the board and I had an epiphany. I realized that every single chip and component on this board is still available today, except for the video chip itself. And I sat there and I thought about it for a while, and I realized that we could essentially build a VIC-20. Now this would mean going back to the 6502 processor, and of course our VIC-20 would have a lot more RAM, better video, and better audio, so it wouldn't have any of the shortcomings of the VIC-20, but it would have the advantage that it's a known working design, which greatly reduces the amount of untested features. The VIC-20 design also has another important aspect. It's super simple. And that was always one of my goals. I wanted the computer to be easy enough for a single person to understand the whole board, and I wanted it to be easy to program. Just as an example, if you look at the C64 memory map, the first 32K is pretty easy to use, but then the rest of the RAM is all shared with different things, and using the last 12K of RAM is actually a real pain in the rear. By comparison, if you look at the VIC-20 memory map, there's no banking. Everything stays exactly where it is all of the time. The bad news is you can only usually get about 32K of RAM in a VIC-20, so obviously we would need some way to increase that. I also need to explain how a VIC-20 or C64 handle their video RAM. You see, the memory in these computers runs at 2 MHz, and the CPU takes turns with the video chip accessing the RAM on alternating clock cycles. So the CPU runs effectively at 1 MHz. This also means you need to have room in your memory map for video RAM and character ROM. However, since our video chip will use its own RAM, this whole setup is unnecessary. This frees up a lot of the design. Now, when you look at the crystal that runs a Commodore 64 or VIC-20, the speed of these crystals is often based on the NTSC or PAL signal frequency. So, for example, the NTSC version of the C64 has a clock crystal running at just over 14 MHz. This signal is divided up with logic chips to produce the color subcarrier frequency, the dot clock, the memory bus speed, and eventually the CPU speed, which, as I mentioned, runs at half the memory bus speed because it alternates cycles with the video chip. And it's also important to realize that other chips like the SID chip and the CIA chips have timers and all work off these frequencies as well. That's why it's nearly impossible to overclock a computer like this, as all of these things are dependent on that main clock signal, and messing with any one of them can cause significant problems. However, since the Commander X16 will be using VGA and the video chip is going to have its own clock, the speed of the CPU is less constrained, and the 65C02 is technically rated at 14 MHz, but we knew there would be other chips on the board that might present a bottleneck, such as the RAM and ROM, so the goal was to run it at 8 MHz. Now, failing that, I'd be totally happy with 4 MHz and could even live with 2 MHz if it came down to it. As such, this is the memory map I came up with. You get almost 40K of base memory, which we're calling low memory in our design. And then over here we have another 8K, but what makes this area special is that it's banked. And the banking system for this is so much simpler than what the C64 uses. You see, there's 256 banks of 8K each, giving a total memory area of 2 MB. Now we're calling this area the high memory area. The entire 16K ROM also banks, and there are 8 possible banks for this, allowing us to cram a lot of built-in applications into the system. Now, there are some things I should mention about this design. A lot of people will look at this 39K area here and say, that's all? But the reality is, this is more than a lot of people might realize. For one thing, this RAM is all available. Other similar computers of the era would also have to incorporate video RAM into this area, which could be a lot if graphics mode were to be used, and as I mentioned, we don't need that since our video RAM is separate. Second of all, our computer doesn't need to load any sort of DOS into RAM like an Apple II, Atari, or an IBM would have needed to do. Another consideration is that BASIC requires contiguous memory area, which means that this area here is all that can be used by BASIC directly, so we'll have a similar amount of available BASIC RAM as a Commodore 64, which boots up with 38K free. And to be honest, I've almost never seen anyone use up the entire 38K in a BASIC program. It's actually really hard to do. I'd like to draw your attention to the memory map I showed for Planet X2 a while back. The entire game code actually fit in the first 16K section of RAM. Actually, I think the game code was really something more like 13K, and all of the rest of the RAM was used for things like graphics and music and playfield map and variable data. If I were to design that game for this computer, for example, I would be able to use this entire area for code, which is 3 times larger than what I had available on the Commodore 64. And all of the other data could go into this banked area. Now, let me explain how these RAM banks are controlled. It's ridiculously simple. We've just taken one of the 6522 chips and used an entire 8-bit I/O area and connected these to the upper address lines of the RAM chips. So you can literally just type POT 40801 and then any number between 0 to 255 to select your RAM bank. Or if you're doing this in assembly language, you would just need 2 commands, LDA with your RAM bank number, and then store that to 9F61. So it's super fast and easy to select RAM banks, and there's up to 2 MB of high RAM available. Once we had a plan for the board, then we really needed a better long-term video chip solution. So I reached out to the community, to some people who were FPGA experts, to see if they could design a custom video chip. I only had a few requirements. I said I wanted it to output VGA video, and I wanted it to use its own RAM, and I wanted it to interface to the system bus through 4 registers, so it would essentially occupy 4 bytes of system RAM. The first byte is the auto increment value, and I'll explain this in a moment, and then next you have the high address byte and then the low address byte, and then the last you have as the read-write byte. So if you wanted to write to the first byte of video RAM, you would set these 2 values to 0, and then you could write the value you wanted to put in there to this register. And you can also read this register to find out what byte is in there. Now at first, this would appear to be slower to use than a setup like the C64, where the video RAM is shared with the CPU. However, that's where this auto increment byte comes in handy. If you set this byte to 1, then every time you write a byte to this register, the value in these registers will automatically increase by 1. So you can set the starting location and just keep writing bytes one after the next. And this means that when doing block copies of data to and from the video chip, it's actually just about as fast, and in some cases faster, than using shared video RAM. I ended up getting working submissions from 2 different people. Ross Andrews sent me this daughter board here, which we codenamed Project Vulcan. And then Frank Vandehoof sent me this little video board codenamed Project Vera. Now in the beginning, these boards only had text modes, which was fine because I said that's all we needed to get started as long as the bus interface worked. Now both of these boards worked, so we ended up having to select one going forward, which wasn't an easy decision. We ended up selecting the Vera chip for the long term. Now Frank had already designed a small single board computer he called the Kaneko, which means kitten in Japanese, and it already had working VGA output, so he was able to use a lot of that experience to design the Vera chip. One of the first things we needed to do was get the Vera chip connected to a Commodore 64 so that we could start testing things. Kevin built this little board where the Vera daughter board can just connect in like this, and then we can plug in a VGA monitor and plug it into the C64's cartridge port. Of course, it didn't work first time. As always with these things, it took a bit of debugging, but we did eventually get it working, and you can see it here working on the C64. It was really important to be able to see the chip working on a C64, not only so that we could prove that the FPGA design worked and was compatible with a 6502 processor, but also so we could start developing kernel code that would eventually make its way into the final production board. In fact, we've talked about making this into a separate product for the C64 users once all the FPGA design is complete, which would give all of the Commander X16's video features to C64 users, or heck, even VIC-20 and PET users for that matter. So what is this Vera chip capable of? Well, for starters, it has several text modes, starting with the 80x60 mode, and can go all the way down to a VIC-20-like resolution of 20x15. Text mode works in 16 colors with a user-definable palette, although the default palette mimics the Commodore 64. However, unlike the Commodore 64, you can define both foreground and background color for each character. And there's also a 256 color text mode, as well as special tile modes. There's also a 4-color, 16-color, and 256-color bitmap mode with a master palette of 4,096 colors to choose from. It also has features such as smooth scrolling, multiple layers, and sprites. It also has 128K of dedicated video RAM. This will put the Commander X16's video capabilities very much in line with the Amiga, actually superior in many ways, and even superior to VGA graphics as well. This is actually far more than I really ever even wanted for the system, but the main thing is it works. Now, at this point, the main people working on this project was evenly split between myself doing kernel development, Kevin Williams doing the board design, and Frank Vandehoof doing the video chip. However, in searching for help with the kernel, I ended up contacting Michael Steil, who's an expert with the Commodore kernel, and he became excited about the project, and so he jumped on board. And to be honest, most of the heavy lifting in this project is now being done by these 3 people. And so, while this is still my dream computer, don't for a moment think that I'm designing this by myself. In fact, quite the opposite. In fact, I have somebody working on a custom case and 2 different keyboard solutions, including a low-end keyboard and a high-end keyboard with mechanical switches, and a user manual. And that person would be Christian Simpson, better known as Parafractic.
Thank you so much, the 9-bit guy. The extra bits for parity, right? She's bored already. But yes, Parafractic here from Retro Recipes. And you may know my channel for Puppyfractic or Ladyfractic's repairs. Or of course for my full-size working LEGO Commodore 64, the Brixty4, which I designed and built. and it's on the subject of design as to why I was brought on board to the Commander X16 team. And the first challenge we set ourselves was looking at the logo. So basically, I see the Commander X16 as being about rebirth. It's the first of a new breed of retro machines. And it was about the time that we were looking at the logo design that we had this butterfly invasion here in California. So here is the Commander X16 butterfly logo. As you can see, we've tried to incorporate modern elements like those sharp cutting edges and the modern font, but with the juxtaposition of the old school color gradient. And we were able to work with David to take a version of that logo to the basic screen. But what else can we put the logo on? Well, that brings us neatly to the subject of the case. And in this case, pun intended, I didn't want to reinvent the wheel. There are so many great cases out there already that we could actually rebrand, rewrap, and customize. So that's what I'm doing, and I'm already working with a company on that. And here's the first sample. So this is going to be for the mini ITX version, which is going to be released a little way down the line. Now, micro is weirdly bigger than mini, although Lady Fractic assures me size doesn't matter. But we are going to need a micro ATX case first. So I've also worked on a design for that. Here's the mock-up of it. We're not sure which color to go yet. We'll probably put this to a poll on the Facebook group. And I've kind of put a little Easter egg nod there, or a tap on the shoulder, on that front panel. It doesn't just show you where the power button is. If you read it a certain way, it actually says 8-bit power. But to me, a lot of that power comes from the nostalgia. But this case won't just be nostalgic. We're going to make sure that in the back you've got lots of room for expandability and any of your own hacks that you want to do. So what about the keyboard? Well, again, we're going down a standard route, but rebranding and rewrapping it so you get the best of both worlds. And here's a little mock-up of how it might look with those Ps2 characters in place and the logo on the top. And also on the team, we're lucky to have Andrew Owen. Yeah, you like him, right? He's looking at the possibility of a deluxe, all-singing, all-dancing keyboard using Cherry MX micro switches. She loves those. Well, that just leaves the user guide. And for this, my one prerequisite is it must be spiral bound. And I know David's in agreement with that. So we're already well into the process of producing that. And it'll be kind of like the old school VIC-20 user guide or the basic programming guides of the 80s with lots of illustrations and easy to follow along basic programs. Well, that's about it for the updates on the exterior design. Okay, all right. I put a treat in there. You can take it. Do follow along on the Facebook group though, because I do post updates there and polls asking for your opinion from time to time. And I might even post some updates on my YouTube channel. But for now, from me and Puppy Fractic, back to you in the studio, the 8-bit Murray. Bye.
Okay, thank you, Parafractic. Now, let's talk about sound chips for a moment. So this was a really difficult decision because I wanted a chip that was still in production and that would interface with a 6502 processor and was easy to program for. Now, what I mean by easy to program is if you look at the Commodore VIC-20, which is the computer I learned to program on, I could simply poke a value to one of the 4 sound generators and immediately get sound. It was that easy. When moving to the Commodore 64, however, making the SID chip do anything required a lot of setup, which was often annoying when I just wanted a beep or two. However, much like the video situation, there really wasn't much available that seemed appropriate. We ended up selecting the General Instruments AY3-8910, which is the same sound chip used in a lot of systems from the 80s, including the Sinclair Spectrum, the Intellivision, the Vectrex, the MSX computers, the Mockingbird for the Apple II series computers, and the Atari ST. And while these are inferior to the SID chip found in the C64, we figured we could partially make up for that by including 2 chips, giving us 6 voices. And here's a sample of what that might sound like. You can find a lot more samples on YouTube and SoundCloud if you want. So, to test these chips, Kevin also designed a board for the C64's cartridge port that has 2 of the AY3 chips on board. As you can see, it has the 2 AY3 chips, and what you can't see is that underneath each chip is a digital analog converter, or DAC. So that gives stereo digital output as well. I wrote a sample program where I can test the various voices of the chips, like this. It doesn't do anything terribly impressive, but it allows me to test the function of all 6 voices. Now, there wasn't a lot of existing code to use since the AY3 chips were rarely ever used in 6502 based computers. Anyway, everything was looking promising with these chips, but in the end we had to abandon them, which I'll talk more about later. So now I want to talk about my master plan. So much like Elon Musk had a master plan to introduce mass market electric vehicles in 3 different stages, I also have 3 different stages I'm working on. So originally I had suggested that I wanted to be able to sell this product for $50. Unfortunately, that's not going to happen, at least not at stage 1. The first product will be a motherboard designed for a micro ATX style case. The board will be all dip packaged just like a vintage computer, and it will be very hackable. It will have expansion slots so you can add cards and other hardware. Now, this first board is going to lay the foundation of the architecture, and it will be aimed at hardware and software developers, and it's going to be kind of expensive. I don't know an exact price at this point, but I'm thinking somewhere between $200 and $300, and I can't get more exact because we haven't finalized the hardware and we haven't even found a company to manufacture it. In fact, we may be looking at selling the board by itself, or maybe possibly getting a custom case manufactured. It may even be sold as a kit that the end user can assemble, so there are a lot of unknowns. The second stage of this development would be to build a second board that uses smaller surface mount parts. This would reduce the size and cost of the board, as well as most likely the cost of assembly. It would most likely be aimed at a mini ITX style board and be far less expandable and less hackable. But I still don't think that would put us anywhere near the $50 price range I had initially suggested. For that, we would need to condense the entire thing down to maybe a single FPGA with a RAM chip or something. And if there's enough demand, maybe even a custom ASIC. At this point, you'd have something about the size of a Raspberry Pi. So that's the end goal, and whether we get there or not will depend greatly on how the first 2 stages go. Okay, so I've got Kevin Williams from Texelec back with us again, and he is the main designer behind the Commander 16 prototype board, and we've got our first prototype in. So these were actually made by PCBWay. They've been following this project with enthusiasm, and they offered to make our first 10 prototype boards for free, and so big thanks out to PCBWay.
Yeah, they're great boards, good quality. They're going to serve us well for this project.
All right, so I'm going to have Kevin give you a little overview of these finished boards.
This is the first fully populated board that we built to do some testing, and in this empty slot right here is actually where the Vera video module is meant to be installed. Before we installed this module initially, however, we wrote some sample assembly code to do some various tests like flash and LED, test the memory decode logic, as well as the I/O select logic. And once we had written enough code to feel fairly comfortable that the processor was operating and doing what it was supposed to do, we moved into the next phase, which was to test the Vera video module. Unfortunately, that's when we discovered our first issue. The module is actually installed backwards due to a bit of a miscommunication between Frank and I. And after we determined, okay, let's move that module to the bottom, I then discovered that the Ps2 port also had a mirrored image. So this is the board that we actually wound up starting to use. As you can see, the video header is on the bottom, as well as the Ps2 keyboard port. And now we just have to install the board. And this is another board that we made. It's actually the same as the green one. It's just a different color. But now we have a machine that's fully ready to run. Let's just walk around the board real quick and show the different ports and features that are available. First on the right here, we have the Commodore IEC serial port, which is also used for printers and floppy drives on Commodore 64s and VIC-20s. I also have a header on here. Initially I didn't have the connector, but we decided to go ahead and add both of them so we can plug in an SD to IEC or any other floppy drive as we get further in development. Next you'll notice the dreaded 7805 regulator that everyone hates. Put that on there just because I have a lot of them. Ultimately the board will be powered by ATX, so the barrel connector and the large capacitor will be a thing of the past. They're just here for our prototype. On the back of the board, there are actually 3 different connectors that were initially designed for video. We only have 2 of them populated at the moment. The third is S-Video. That's actually planned to come back at some point, but for the moment we don't have the connector installed. The others are, of course, VGA and composite video. Next is the Ps2 Keyboard, which is also installed upside down, as I previously discussed, but working great. Lastly is the audio jack on this side, as far as external connectors go. That will allow you to hear the sound from the AY3 chips. Let me turn the board this way. All right. On the back of the board, we have 4 expansion headers that we put in place just for us to test other functions and other things that we might want to add to the final board. These aren't going to be representative of what the final has. They'll actually be much larger and actually lined up to where they will fit in a mini ATX style case. Just below those are the AY3 8910 chips. Unfortunately, these won't be in the final product. They're just simply not going to work fast enough to run at 8 megahertz. But you'll see 2 small header expansion pins here. The AY3 chips themselves have 2 ports, much like a VIA or a 6522 chip would have. One port is connected to a DAC on either one, and the other is just open. Unfortunately, we will have to migrate this, but the LCD screen was originally installed as a way for us to have some sort of video before the Vera chip was complete. However, as we completed the design of the motherboard and had them manufactured, the Vera board was actually complete right around the same time. So as a result of that, the LCD will also be removed from the final board, but for the moment it works, so we left it on here just to play with it. And later, it's certainly something that could be built in an expansion port if you desired to do so. So let's talk a little about what chips are actually on the board. As you can see here is the 6502 CPU, and just above it is the first of 2 6522 VIA chips. These are the peripheral style chips similar to what the VIC-20 has. And there's the second VIA chip here as well. And just next to it, you'll see a small expansion port that says user port. These pins are actually very similar to the user port on a Commodore VIC-20 or a Commodore 64. Just to the right of that are the 2 jumper settings that control the master clock signals for the system, as well for the AY3. We actually have a 16 megahertz crystal and 2 chips that just divide down to different frequencies. We can actually set the master clock anywhere between 16 and 1 megahertz, and the AY3 clock in this case with the 16 megahertz crystal from 4 down to 1 megahertz as well. This won't be on the final board either. It's really for us to test, and as you can see, we're actually running at 2 megahertz right now. And there's some various reasons for that, but as we're progressing, we hope that the board will actually be able to get up to 8. Just below the video card header, we have 2 ports labeled NES/SNES ports. The reason these are here as pin headers at this point is we haven't decided what physical port we're going to use on the final product. But for now, we can actually take a game controller and modify it so that we can connect it on here for testing. The last section to talk about really is at the bottom here. There's the ROM chip and the main RAM for the system. The first chip here is 128K and contains actually 8 banks of 16K, which is available as the top section of the ROM. The bottom 48 or 40K of memory is actually stored on this chip, which is just a physical SRAM chip. And these 4 chips are the 2 megs of RAM, which are banked in the A000 area of RAM. Lastly, at the bottom, we have an NMI as well as a reset button. We will have a reset button in the form of the case. It's not clear if we're going to have an NMI button on the case, just mostly because cases don't have 2 buttons often. But we may have the ability to add one with a pin header if you do choose to have one later.
Now I'll give you a quick little demonstration of the prototype board actually running. I'll just plug it in. And there it is. I don't have any way to load anything yet since the disk drive routines aren't working yet, but I can type stuff in BASIC, and I'll type in the famous little random maze program. So as Kevin mentioned, it's only running at 2 megahertz right now. However, I can at least say it's very stable. I've had it running for several days on end without any sort of glitching or lockups. I also wrote a small clock program to test the LCD screen. Okay, so this is the emulator. It runs in Linux, Windows, or Mac, and this is what we've been using to develop the kernel with, but now we're moving more into the software development side of things with it. And I'll just, give you some little examples here. And there you go, same type of thing you might normally do for a little test. So it also runs in 40 columns mode. You can press F4. This is the exact same behavior that the real computer will do as well. So you can go into 40 columns, and of course it preserves your program. It doesn't like reboot or anything like that. You can actually switch back and forth between them just by pressing F4. Okay, so what I want to show you now is, let me clear the screen, and we've added a new command to BASIC. So because the video RAM is stored separately from regular RAM, you're not able to use poke commands, at least to directly modify video memory. So we added a new command called vpoke. And the way this works is you put in the bank number. There's like 4 or 5 memory banks in the video card. We're going to use bank 0. I'm going to use location 0, so that will actually correspond to the top left character on the screen. And then I'm going to put in a 1, which is the letter A. And as you can see, it will poke that right to the video memory. And you come over here and change it to 2, and then you got a B and so forth. Now the video attributes, the color attributes, is actually the next byte after the character. So if we go to byte 1, then you can see it changes the color attribute. And then you can do this backwards. You can do print, oops, not peak, vpeak, and then you can put in bank 0, comma 1, and it should return 2 because that's what's in video RAM at that spot. So that's vpoke and vpeak. We also have a monitor. Wouldn't want to show you a whole lot about this because I'm not sure that we'll be able to use this monitor because I don't know if we have the rights to it. And we have a different monitor that we're working on, which I'll show you later in the video. So I will, I will exit out of that. Now I want to show you a couple of programs that have been written using the emulator here. I'll start off with my own program, PetDraw X16. And by the way, you don't need a comma 8 or anything like you would on the C64 because if you leave it, at least on the emulator anyway, if you put no drive, it defaults to device 1, which is of course the local file system where the emulator is, whoops. So there we go. Alright, so this is written entirely in assembly language. Okay, so this is PetDraw. I kind of rewrote this from scratch just for the Commander X16. It's pretty similar to the Commodore 64 version in the way it works, but obviously it takes advantage of a lot of the new hardware. So you may be wondering, well, gee, what's PetDraw? Well, if you push F1 and go into draw mode, you can press enter, you can pick like any of the characters from the Petsky character set, and you can just, you can just put them on the screen like that. And you might think, well, that's not all that useful or interesting, but actually it is. Now I'll show you why. So let me load in an example photo. I haven't had a chance to do much artwork because I've been too busy writing the program, but I did write one test picture. And here we go. Now I'll load that in. It's just the Commander X16 logo. Not exactly the same one you see on boot up. It's a little bit bigger, but so let me show you one of the neat features here. So you can push F5 and select a screen size, and it actually changes on the fly as you scroll through to these different sizes. So yeah, you can go all the way up to the big, huge text characters up 20 by 15, which kind of look like Commodore VIC-20 characters. Here, let me write some text. So you can see, yeah, it's pretty big. So you also have features where you can, like I can shift whole pieces of the screen, either left, and they'll loop all the way around. I can also go right. You can also go up and down. It's almost like playing with Rubik's Cube, but it's handy for moving stuff around on the screen. Now you might ask what use this program has. Well, the main thing is when I design other software, a lot of the times I need to design or figure out how things are going to go, where they're going to be placed on the screen. For example, like, I push the help screen in here and it pops up this screen. Well, I actually designed the help screen in PetDraw. So the same thing, for example, when I pick the color screen. I mean, I designed this screen in PetDraw, and when you design software, you're going to need to design little screens like this, and it's just a handy developer tool for me, I've always found. So that's the main reason I designed PetDraw. Okay, so now I want to show you this neat little demo that was somebody on the Facebook group posted just a couple of days ago. Sorry, I don't even remember what the guy's name was, but it's probably the coolest demo on the system so far. It's called Green Space, and as you can see, it's all written in assembly language, and this is what it does. So yeah, you got like the little matrix effect there, which is actually pretty cool. Neat little demonstration of the text mode. Now what they're actually using here is, you notice there's a lot of shades of green here. So they're actually using the 256 color text mode. Either that or they've redefined the palette on the 16 colors. I'm not sure, but either way, neat little effect. The next program I want to show you is Tile Demo. And this is actually written in BASIC. And it just does that. So what I can do is I can actually list the program here, and I can run this little demo. And one of the things you can do is you can see it draws this graphic over the text, and it doesn't, it's not destructive to what's on the screen, and that's because it's actually using a different layer. And that's one of the neat things about the Vera chip is it has 2 different tile or bitmap layers, so you can do neat effects like this, which will probably be really cool for some 2D games later on. Okay, so the next thing I want to show you is called mode4demo.prg. Now this is going to demonstrate one of the tile modes. So this is the 256 color tile mode. Now it doesn't move or anything like that. It's just a still image, but this is using 256 color tiles. It looks obviously very reminiscent of Mario. This was actually designed by Frank, the guy who made the Vera chip. So anyway, it looks really nice. And this is actually running in one of the lower res modes. It can actually do higher resolution than this, but this would be the perfect mode for games like this. So alright, moving along, I want to show you Mode 7 demo. Now, I'm going to warn you, this demo only half works. So this is a demonstration of the 256 color bitmap mode of the Vera chip. Now you may be wondering, well, gee, why does it only show half the screen? Well, that's because it has to load the picture into low RAM and then copy it up to the video chip, and there just isn't enough low RAM to copy the whole picture in 256 color mode, so he's only loading half the photo. Now, obviously, what you would need to load a whole still photo into video RAM is you would need to design a custom loader that loads a separate file from disk and then copies it directly into video RAM, which we just don't have yet, but that'll be coming. But anyway, you can get a kind of an idea of what the 256 color mode will look like. Eventually, I'd like to work on a basic editor that works similar to the text editor on the Maximite computer, where you have labels and you can scroll up and down. I also had the idea for an assembly language monitor that sort of blurred the lines between a monitor and an actual assembler. And this was something I hoped could be included in the final ROM with the product so that you could actually write assembly code on the actual computer. And so I talked this over a while back with Michael Allison, and he got to work on developing the software for that. And here's a little video he made showing you the progress he's made so far.
Hi, Mike Allison here with the Commander 16 assembly language environment. We want to make assembly language as fun and as accessible as BASIC is. This new environment is going to give you the ability to dynamically examine your code, write code online, insert, edit, and delete instructions. This example program is showing that we support labels both in place and as arguments for the instructions. The interactive debugger will allow us to examine memory, set breakpoints, and see their values as the application runs. We also support a lot of the traditional functionality of a normal monitor, examining and modifying memory contents as an example. There's a lot more to come, so stay tuned.
So hopefully when this product is ready for release, it'll be possible to program it in multiple different languages, including BASIC and assembly language, right on the computer without needing any sort of cross-compiler from a more modern computer. But now let's talk a little bit about performance. To give you an idea of the speed difference between the C64 and what we have here, I'm just going to use this basic program I wrote. It's a pretty simple program. As you can see, the whole program just fits on a single screen here. And when you start the program, it switches to 40 column mode and then asks how many balls. Well, let's say 5 for this demonstration. Now what it does first is fill the screen with balls, and then it colors them black. Now the reason behind this is that it's faster if all we have to do is update the color attribute and to move the balls around. Anyway, you can see what it does here. Nothing terribly exciting. And keep in mind this program is written in BASIC, which is always going to be pretty slow. But let's see how essentially the same program runs on the Commodore 64. Again, we'll choose 5 balls. And it takes quite some time to draw all the blank balls on the screen, so I'll skip ahead a bit. And there we go. Now you can get an idea of the speed difference between this and the C64. So imagine for a moment a game like Space Station Oblivion. Now this is how fast it really runs on the C64. It gets about 1 frame every few seconds. It's terrible. But with the miracle of video editing, I can speed this up 8 times just to get an idea of how it might run on the Commander. But it would actually probably be better than this, and the reason is the way the C64 handles its video RAM with color cells and an awkward memory layout, it requires a lot of extra calculations to deal with that. But the Vera chip in the Commander X16 is a much simpler layout, meaning games like this would be easier to program and run faster. So what could I compare this computer to in terms of raw performance? Well, one thing to keep in mind, the 6502 processor at 1 MHz runs almost as fast as a 4.77 MHz IBM XT. And the reason is that a 6502 does a lot more work in a single clock cycle. And since our chip is going to be running at 8 MHz, that would be similar to a 32 MHz XT, which never existed, so probably a better comparison would be a 286 running at maybe 12 or 16 MHz. So I think there'll be no problem designing games that you would have expected to see in the 16-bit era. In fact, I wouldn't be surprised if somebody could get something like Wolfenstein 3D to run on this thing. There's something else I want to say. The Commodore 64 can definitely do some fun and impressive games. However, one of the reasons that development for this platform is probably not greater than it is has to do with how hard it is to write games like this. You see, games like Sam's Journey here are using nearly every trick in the book to make this work on a C64. You have to be literally a C64 programming god to accomplish this sort of thing on a C64. Now, I wanted the Commander X16 to be a bit more powerful so that regular coders would be able to write fun and impressive games without having to spend 10 years learning every trick of the book. Okay, so let's talk about the sound chip situation. It turns out the AY3 chips really aren't designed to work on a system bus operating at greater than 1 or 2 megahertz. Now, this should have been obvious to us when we started work on this thing. Looking in hindsight, after all, if you look at the Mockingbird card for the Apple II systems, they actually use 6522 I/O controllers as middlemen to talk to the AY3 chips. However, this is not something I wanted to do because it makes programming for the chips more complicated, plus it adds additional parts and expense to the board. And while we have the AY3 chips working on the board right now, that's only if we keep it jumpered at 2 megahertz. And believe it or not, the same issue is true of the LCD screen. It also won't work reliably past 2 megahertz. So that's another reason this will have to go. You could still interface one of these, but it would also need some sort of middleman, so to speak, so that communication could be slower. So we started looking for other options for sound, and some other options being investigated right now is the possibility of the Yamaha YM2151 chip, which was used in the Sharp X68000, many arcade machines, and is a close relative of the sound chip found in the Yamaha DX27 and DX100 keyboards. Now, this is an 8-voice, 4-operator FM chip, and here's a sample of what the chip sounds like. Now, these are technically not made anymore, but there are quite a few old stocks still available, and worst case, there is an FPGA card available too in case we ever ran out. So Kevin just now produced an expansion card for this chip, and we're about to start testing to see if it will work at 8 megahertz. Other options include the SAA 1099, which was most famously used in the Creative Labs Game Blaster, and it was also an add-on chip for the Sound Blaster. And so this doesn't have the best sound ever, but if we used it, hopefully it would be in combination with the FM chip. That way there would be an easy-to-program sound chip for simple sounds, and something more advanced for those that want it. If either of these fail to work out, Frank has also said he could add some sound to the Vera chip that would give it an 8-channel sound system that would sound similar to the SID chip in the Commodore 64. So we just don't know yet where the sound will wind up, but whatever it is, I think you'll wind up liking it. And we plan to have a stereo DAC as well, no matter what sort of sound chip we come up with. So doing things like mod tracker music should be within the scope of this machine. There are still some challenges ahead, so before you start yelling,
"Shut up and take my money!"
let me tell you about a few of the possible setbacks. So I know I've said the product would be using the 6502 microprocessor, and our prototype certainly is, and honestly that's good enough for me. However, we plan to experiment a bit more with using the 65816 processor like I mentioned before. However, if we use this processor, it will be with the current design, assuming it works at all. Now what I mean by that is we would not be using the full 24-bit addressing system, so the CPU would still be limited to 64K of address space. However, it would allow you to do 16-bit math internally and 16-bit copy operations, which could greatly benefit certain applications. At this point, I cannot say for sure which CPU it will have, but the good news is if you target your code to the 6502, it'll work either way. And the last thing I'd like to bring your attention to is the Commander X16 Facebook group. Now you can find the link down in the description, and this is a place where regular people can find updates and post questions about the project as it goes along. I'll also take this opportunity to mention there is a Planet X3 Facebook group as well, which I forgot to mention when I did the last episode on Planet X3. And so if you're a fan of that game and want to chat with others about it, I'll add the link for that one as well. Also, if you want to see the Commander X16 prototype in person and up and running, I'm going to have this on display at the Vintage Computer Festival in Elmhurst, Illinois in just a few days' time, and there is a link in the description to that as well. And that about wraps it up. Obviously, I will be doing further updates as progress evolves on this computer, so stay tuned for that, and thanks for watching.